carbon is one of the most abundant elements in the universe and serves as a common element for all living organisms. The carbon cycle, like the nitrogen and water cycle, is vital for sustaining life on Earth. It is the biochemical cycle by which carbon is exchanged among biosphere, pedosphere, geosphere, hydrosphere, and atmosphere. Carbon sequestration is carbon capture and long-term storage of atmospheric carbon dioxide. Above-ground biomass is the total biomass of organisms in a given area of volume above the soil. Measuring the amount of above-ground biomass can aid in determining the amount of carbon stock or carbon stored in the forest ecosystem. Growing greenhouse gas CO2 emissions due to human activity is beginning to negatively impact our natural environment and cause climate change. In response, the global community is focusing on controlling the net release of greenhouse gases, mainly carbon, from both fossil fuel sources and from changes in the terrestrial carbon stocks. The current methods for calculating above-ground biomass of forests have limitations in their statistical precision and accuracy. More accurate estimates of biomass are needed in order to inform policies regarding forest management. For our project, we focused on LiDAR data and created various elevation models of the Sagehen Creek study area, located 8.4 miles north of Truckee in Nevada County, California. Sagehen Creek is currently a UC Berkeley research facility and in 1951 signed a long-term special use permit with the USDA Forest Service. The objective of the project is to use LiDAR data to accurately measure above-ground biomass in the study area. These results will be compared to existing data to validate the use of blast tools and fusion in processing and analyzing the LiDAR data. Our research question is, can we accurately measure above-ground live biomass using a statistical analysis of airborne LiDAR data? The existing data was obtained from a previous 2012 project by Q. Chen et al. We obtained shapefile data from the Sagehen Creek study area and vegetation types derived from aerial photographs from the USDA Forest Service from the year 2005. We also obtained field data collected from the 523 random plots between the years 2004 and 2006. LiDAR data was collected in 2005 from the study area using an OPEC ALTM 2050 system on an airplane. Once all the data was obtained and organized, the first step in our methods was to convert ASCII text files to LAS binary formatted files. ASCII files are the raw LiDAR text files that need to be converted to LAS format to be used with the Fusion LiDAR software. After processing the data, we use Fusion to generate a digital surface model of the study area, a digital elevation model, or ground surface model, which was then used to create the canopy height model for the study area. Next, we applied a 30-meter buffer to the plot point data and clipped the LiDAR data once more to show only the plots. Again, Fusion was used to create a ground surface model and a canopy height model for the plot sites. The canopy height model was then used to generate canopy height metrics using Fusion's Canopy Maxima tool. Finally, using RStudio, a multiple regression analysis was used with the above-ground biomass calculated on a plot level to derive an equation that represents above-ground biomass with the LiDAR data. Using R, we found a two-variable regression equation using mean tree height and number of trees per plot, which gave us an R-squared value of 0.96. Using the coefficients from these parameters, we were able to generate a biomass map for the study area based off the canopy height model. Comparing the plot level biomass with the generated total biomass map, you can see that field plot biomass is indicative of the generated biomass map. Using zonal statistics, we calculated total above-ground biomass and got 7.22 times 10 to the 7th megagrams. In conclusion, using LiDAR data, we were able to generate measurements and map above-ground biomass for the Sagehen Creek study area. Last tools and fusion were successful to producing and analyzing the data. These methods can be applied to most forested regions, which can be useful in managing carbon stocks and providing information for environmental policy.